All right, people, how's it going? Today we are going to meet a new kind of function. I think the last new type of function that we will meet this semester. And get ready, because these ones are a little bit awkward. These are called logarithmic functions. So this first example here is kind of a motivator as to why we might want logarithmic functions. So they ask us to solve this equation. 2 to the x equals to 8. And so maybe we'll just solve it right now by just guessing. So I know 2 to the 1 is 2, and 2 squared is 4, and 2 cubed is 8, right? That is 2 to the 3. So x equals 3 is at least one solution of this equation. I think we know, too, that since 2 to the x is a one-to-one function, that there is only one solution. There is only one place where 2 to the x crosses the line y equals to 8. So this is, in fact, our only solution. But still, we would like some kind of algebraic way to sort of cancel out what we call this exponentiation. When you raise, when you say 2 to the x, that's like saying exponentiating x with base 2. We'd like an operation that undoes that, right? We'd like some kind of inverse operation. So what are some other kind of inverse operations you've thought about? Like the squaring function, x squared, it's undone by taking square root, right? Or the function that adds 1, its inverse is the function that subtracts 1. So we'd like some kind of inverse operation for this exponential function. And that is going to be brought to us in the form of what they call logarithmic functions. So look here at the definition. So if x and b are both positive real numbers, where b is not equal to 1, then y equals to what they call log base b of x. This is a function of x. The name of the function is log base b. And what is its definition? Well, log base b of x equals to m exactly when b to the m equals to x. So the way I like to write it here is to circle the letter b and say that b to the m equals to x is the same thing as saying log base b of x equals to m. These are supposed to be equivalent statements. So this is defined to mean the same thing as this. What is the difference here is that we are able to now write the exponent on the left side, b to the m. We're able to bring that one downstairs and write it downstairs on the other side of the equation, or on the other side of the sort of equality of implications. So that could help us solve an equation like this one up here by taking the x and bringing it downstairs to live with everybody else, so that we could isolate x and get x by itself, right? X equals to ultimately 3. So this equation up here that says 2 to the 3 equals to 8, that's the same thing as saying log base 2 of 8 equals to 3. So let's do some examples here. So we'll convert the expression 7 squared equals to 49 to logarithmic form. What that means is that if 7 squared is 49, that means log base 7 of 49 equals to 2, right? Because 7 to the 2 equals to 49. Okay. How about the equation 4 to the p equals q? Well, this one is a little bit, more just abstract or something, because there's no concrete numbers here, but we can write this one as log base 4 of q equals to p, because again, 4 to the p equals to q. Okay, now maybe let's go backwards. So log base 9 of 3 equals to 1/2. What does that mean? Well, that means that 9 to the 1/2 equals to 3, as we've written here. And now if you recall, from long ago, closer to the beginning of the term, what it means to have this sort of rational exponent up here. What this really means is the square root of 9 to the 1, or rather the square root of 9 equals to 3. Okay. Last one here. They ask us to convert log base c of 8 equals to 2r to exponential form. Again, this one's a little bit more abstract. We'll just kind of follow the rules at hand so that c to the 2r equals to 8. Okay. So let's see. Let's do a couple more concrete ones here. I like this next example, example 6. So they ask us to find log base 2 of 16. Well, 2 to the what equals 16? 4. 2 to the 4 equals 16. Okay. They ask us to find now log base 12 of 12. Well, ask yourself, 12 to the what equals to 12? 1, right? 12 to the 1 equals to 12. Very nice. Okay, the next one is log base 5 of 1. Well, for this one, ask yourself, 5 to the what equals to 1? Oh, I know. It's 5 to the 0. 5 to the 0 equals to 1, right? For any of our bases that we had b, it was always b to the 0, always equal 1, right? So in this case, the base is 5, so there's no different. 5 to the 0 equals 1. So log base 5 of 1 equals to 0. Okay, and these last two are pretty tricky, so buckle your seatbelts here. They say log base 1/2 equals to, or log base 1/2 of 4, sorry, equals to, I don't know. Well, ask yourself, 1/2 to the what equals to 4? Well, I guess, I'm giving you the answer right here, that's fine, but let's think about why -2 here is the answer. Well, if we do 1/2 to the -2, that is to say 1 over 1/2 squared, that is 1 over 1/4. But 1 over 1 over 4 is simply 4. So log base 1/2 of 4 equals to -2. Okay, and this last one here, they ask us for log base 5 of 1 over 25. I think this one's maybe a little bit less awkward than the one above it, but that's fine. This is also -2. Why? Because 5 to the -2 equals to 1 over 5 squared, which equals to 1 over 25. All right. And so there's two bases for logarithms that we'll probably see often. I think one we'll see a little bit more often than the other. But what they call the common log, which is base 10, so it's like log base 10 of x. This one they like to abbreviate by just writing log, with the assumption that when there's no base written, they mean base 10. Okay. I think this kind of comes about from our desire to sort of base everything in terms of 10 when we write our numbers, right? So they call this one for that reason the common log, because it's common for us to think of numbers as broken up into powers of tens, right? Like ones, hundreds, thousands, etc. Okay. And the base that we'll see actually probably most often when we're dealing with logarithmic functions is what's called the natural base. And that is that same one, e, that we met before, 2.7 whatever, right? So this one, when we write log base e of x, the shorthand notation that they write for that is ln. So that's supposed to be an L and an N, giving us natural log, okay? So if you see that, ln of x, that just means log base e. So maybe we'll see a couple up here. They ask us to compute log of 100. That is log base 10 of 100. And so ask yourself, 10 to the what equals 100? It must be 2, right? 10 squared is 100. Okay, and this next one's really fun. They write ln of e to the 5th. That is natural log of e to the 5th, or rather log base e of e to the 5th. Well, ask yourself, e to the what equals e to the 5th? This is almost a trick question. The answer is so simple, right? E to the what equals e to the fifth? Well, then the what must be 5, right? Because e to the 5 equals e to the 5. This is almost saying nothing, right? So here the answer is natural log of e to the fifth equals to 5. Notice here how these two operations seem to undo each other. This exponentiation of doing e to the 5 and then followed by doing natural log just undoes everything and leaves you with just 5. This is exactly what we want and exactly how we'll go back and try to solve that equation from the beginning, maybe at the end of this lecture. So then the last 3 examples here are just asking us to use a calculator somehow. And that's an option you have in the Texas Instrument, and you can do that. But these aren't too terribly enlightening, so we'll kind of leave them for now and come back in the next video and learn a little bit more about logarithms, namely some very important basic properties of them. So we will see you then.